All right, BC. This should be our last-ish screencast. Last-ish. There'll be another one probably where I go over some answers for homework. But last one with new material. So, we've seen this Taylor series, that term be branded about throughout our travels, and Miss Yam and I have just referred to it, saying if we ever see the Taylor series about x equals 0, then we can just say that's the Maclaurin series. And so the Taylor series we want to think of as being the general form of the Maclaurin series. The Maclaurin series, we realize, is really good at approximating things at x equals 0, but maybe not so good if we wanted to move out, unless we had a whole lot of terms. So the Taylor series is going to be more general. And so if we just really quickly again thought about how we came up with the Maclaurin series, right? Let's just say we wanted to approximate this really well. Instead of at x equals 0, we said x equals 1 is where we wanted to approximate this. So if we think about our successive polynomials and the things that we want to have in common with whatever function I drew over here with this green curve here, right? The first sort of naive, right? My first attempt to approximate this would be my polynomial would have my first attempt at p of x, right? We'd want to have the same value there. So that might just be equal to, let's say this thing is some f of x, it would just be equal to f of 1, right? That would be this nice horizontal line that sort of went through there, and it would be a pretty bad approximation, right? The next thing that we'd want to say is, what if their first derivatives and that value, what if they were both shared in common, right? And I think you guys can probably see where this is headed, right? That my second attempt would look something like this. And now let's think about why that is. Well, if we think about at x equals 1, right? P of 1, it would share the first, it would share the value, right? It would share the value because when x is 1, that second term would be 0, because that x minus 1 in there. And when, if I were to take its derivative, everything would go away except for f prime of 1. So it would also share its first derivative. And that would be the local linear approximation at x equals 1, right? So that would be something that looked like this, right? Something that looked like this. I don't know. Anyway, I didn't mean for this to end up being like a point of inflection, but it sure looks like that. And then we could go on and on and on. Where my third attempt, where I'd want them to all be the same through the second derivative, my f's got less fancy there, would be something that looked like this, right? We're going to have the x minus 1 squared, and yes, if you were thinking about it, yes, of course, we do need this 2 factorial, and really we had this 1 factorial and the 0 factorial, but that's a little silly to keep writing. Okay, so we can see that in general, we could expand this out, and it's sort of exactly what you think it would be. At x equals 1, sort of all the other terms will float away, right? Because that's what we're after. And when we take successive derivatives, right, only one term will matter each time, if that makes sense, right? All the terms to the left of that one will disappear and fall away, and all the terms to the right of them will be 0. So we'll only be left with one term that matters. And it's just like the Maclaurin series, right? So I'm just going to give you the in general, right? We say, we would say, we'd say that the Taylor series, I should probably capitalize that, someone's name. By the way, you should look him up also. Brooke Taylor, I believe, Brook. Also fan of awesome wigs, just like Mr. Maclaurin. Definitely worth your time to Google. The Taylor series for a function f about, that's the key word that we always use, about x equals a, is given by this general mess that I'm about to write here. This general mess, which is going to be f of a plus f prime of a times x minus a plus f double prime of a times x minus a squared over 2 factorial plus f triple prime of a times x minus a to the third over 3 factorial. My voice sounds sicker and sicker as the day goes on. And then the general term, right, would be this f, right? Remember that parentheses with the nth derivative there? X minus a to the n all over n factorial. Or we could say that it equaled the sum from n equals 0 to infinity of this thing. And this is sort of just the general form, and it's going to have all the same properties as our friends, the Maclaurin series. Okay, I just wanted to gently sketch that out as to where this is coming from, and now sort of all of those other questions in S3 will make sense now. Well, we hope. And the other thing I would add is when we say the Taylor series about 0, right, with all those problems that we've done already, right, all those problems that had the Taylor series about 0, that would just mean a is 0. And so you can see that all of these terms here would just be x and x squared and x cubed and x to the n and so on. Okay, so that's just the general formula for Taylor series and sort of where we're going. And, the algebra here could get a little bit crazier, but in general, you're just going to end up with these sort of x minus a or x minus 1 or something, just sort of all fitting together. So I have a joke, because I had to incorporate one, because, Miss Yam put some pressure on me to do so. And the joke is, or the question is, why do Maclaurin series fit their functions so well? So pause me and think of the answer. All right. It's because they are tailor made for them. Haha. Oh, I hope you guys love that one. It's pretty good. It's pretty good. All right. Maybe I'll show my joke next week for our polar coordinates one from last year. That they're tailor made for them. I found that one funny. I'm guessing I have, if they're roughly 60 BC Calc students, I'm guessing I have, probably only 20 of you are watching these, but I bet all 20 of you are rolling your eyes at me. Anyway, let's do a problem together and then we'll send you on your way. So I'm going to do this one, I think. Okay, so we're dealing with the Taylor series for function f about x equals 1 is given by this mess and converges to f of x for when x minus 1 is less than r, where r is the radius of convergence of the Taylor series. So some things to note right off the bat, okay? We no longer have this very, very easy absolute value equation, right? We now have the absolute value of x minus 1 because we're dealing with something about x equals 1. I think it doesn't take a real leap of faith to realize that this radius, this interval of convergence is probably going to be centered at 1 because that's where all the terms would be 0. So anyway, let's start off by going through some mechanics, and this should feel very, very similar and familiar to what we're used to with our friend the Maclaurin series. We're just going to have x minus 1s in there instead of x's. Sorry. So find the value of r. Well, that's asking for the radius of convergence, right? So that's asking us to look at our friend, this limit, right? And we're going to be looking at the nth plus first term over the nth term. So that's negative 1 to the n plus 1 plus 1, 2 to the n plus 1 over n plus 1 times x minus 1 to the n plus 1. So that whole thing all over these guys without the n plus 1, right? So negative 1 to the n plus 1, 2 to the n, and x minus 1 to the n. Okay, so we're gonna do this kind of quickly, right? We're gonna fast forward a little bit. And again, this is gonna find for what values of x would my series converge, right? And so the negative ones sort of fall away, and I'll be left with what? 2 to the n plus 1 over n plus 1. And then we're gonna flip the second guy. We flip the second guy, we're gonna get n over 2 to the n times x minus 1 to the n. Okay, well, the n's can all come out and sort of play nice. So we're going to have the limit. As n goes to infinity, we're going to have a 2 in the top. And I'm just going to have the absolute value of x minus 1 because the n over n plus 1 sort of cancels. There's no more n, so we can forget the limit notation. And I want this thing to be less than 1, remember? So I would say my r would have to be a half, right? Because we're going to have x minus 1 in absolute value is less than a half. So that's where this radius of convergence is, right? The radius of convergence would be 1/2, and we don't have to actually go through and find those actual bounds to see if 1/2 and 3/2 work, right? If they asked us to find the IOC, right, then we're stuck. If asked, we'll say, to find IOC, then you're evaluating, right, we know that it loosely will look like this because we're going a half in either direction from 1, but we would need to examine the bounds, right, to see if they are or aren't included. Okay, so that one was easy and sort of, something that we remembered. Again, this x minus 1 actually didn't end up mattering. It just sort of came along for the ride, right? It would end up mattering to know that these guys were 3/2 and 1/2 and not negative 1/2 and 1/2. But other than that, it really didn't do a whole lot there. So let's think about B now. Find the first 3 non-zero terms in the general term of the Taylor series for f prime, the derivative of f about x equals 1. So if you'll recall, right, in my last screencast, hopefully you watched that one. I can't see why you'd watch this one if you hadn't watched that one. We had 2 ways, right? We could either take the derivative of the individual terms, or we could take the derivative of the general term and then sort of plug in. I'm going to do it the second way because I don't have the individual terms. So I want to take the derivative of this nonsense here with respect to x. With respect to x, and I keep on emphasizing that. We're not taking it with respect to n. All that stuff out there is a constant, so don't worry about it, right? So we want this derivative here to be the sum from 1 to infinity, just like the original thing. This is a constant, this is a constant, this is a constant. Okay, now we're dealing with something that's not a constant. X minus 1 to the n. So power rule and chain rule would just give me 1. So I don't actually have anything. Forget about these guys, they cancel, and I'm left with this expression. Again, we're asked to find the first 3 non-zero terms, right? So we're going to start at 1 and hope that we don't get 0. If we start at 1, I'm going to get negative 1 squared, that's 1, times 2, times x minus 1 to the 0. So just 2. If n is 2, I'm going to get a negative, I'm going to get a 4, and I'm going to get an x minus 1. And then lastly, if n is 3, I'm going to get a positive again, because I'll have negative 1 to the 4th. I'll be left with 8 and x minus 1 squared. Those are my first 3 non-zero terms. And I know you might be looking at this and saying, Mr. Perlis, where's the 2 factorial? We don't need the 2 factorial here. Right? We're just taking a derivative and plugging stuff in, and we were given the Taylor series, and it didn't involve that, so we don't need that mess, okay? So here we are with this series, okay? These first 3 terms. The Taylor series for f prime about x equals 1 found in part B is a geometric series. Well, that's nice that they gave it to us. You'll notice that almost all of these AP problems have to sort of involve a geometric series, because that's really the only thing that we know how to find, in terms of, finding an actual value there, right? We know where geometric series converge to. We don't know them as well for other types of series. So they tell me it's a geometric series, and I see that, right? My R is going to be -2 times x minus 1, kind of a weird thing. Find the function f prime to which the series converges for absolute value of x minus 1 is less than r. So there's a lot to unpack there. Find the function f prime. Well, this is an infinite sum, right? This thing is an infinite sum. This thing I'm highlighting up here. Infinite sum. And we can express that nicely, right? We can say that f prime of x is equal to this a over 1 minus r, which is, of course, 2 over, be very careful here with a lot of negatives, 1 minus -2 times x minus 1. You can take my word for it. That's also 2 over 2x minus 1. I think that's right. There's a lot of negatives going on down there. I think that's right. 2 over 2x minus 1. And so that is an expression for f prime, right? It said, find the function f prime to which the series converges. And again, we only are concerned when the series converges, right? That's what allows me to use this. If my series diverges, I can't use a over 1 minus r, because it would be going off to infinity, right? So we are only concerned when this does converge, so it allowed us to use a over 1 minus r. Okay, so we did that first part, and then they snuck another piece in here. It really should be part D, in my opinion. Use this function to determine f for this interval of convergence. So if this is f prime, well, then f of x is the integral of f prime of x. Well, that's just the integral of 2 over 2x minus 1 dx. And that, of course, right, is what? That's just the natural log of 2x minus 1, right? That gets me the chain rule on the top, right? Ideally, right, like you might be u subbing or what have you, but that's where we can be beyond that and sort of leap beyond that. So this is my function here, plus some c, which we now are going to have to go out and find, right? And so where is my initial condition here that's going to help me? Do we have an initial condition here? I have to plug in something. Well, if we plug in 1, my first term is 0. So I think we know that f of 1 is 0 if we plug it into that very top. So if f of 1 is 0, we would solve and get that c also is 0. So we would just get f of x is the natural log of 2x minus 1. Which would be one of my final answers. I guess this is my other final answer for this part. All right, so there was a lot going on there, but hopefully you guys see that there's not a whole lot to these Taylor series, right? That the sort of the x minus 1 or that x minus a piece isn't going to necessarily muddy the waters as much as you might think it would. So I hope this was good. We did this one already with 3. Again, Taylor series about x equals 0. I'm not 100% sure which homework things I'm going to assign you. I think we're going to do 1, and I would again like to call your attention to be careful here. They're giving it to you slightly differently. They're giving you the nth derivative at a point. They're not giving you the series. They're giving you the nth derivative at a point there. But I think we're going to do 1 and... what was the other one I liked? I think I liked 4. think I liked 1 and 4, but maybe also 5. Oh, I'll post that and give it to Miss Yam, and then I'll post some homework answers in another screencast form. All right, I hope this was helpful, and you enjoyed my joke. So good.